that 2 squared is how much? 4. 2 cubed is how much? But 2 to what power will equal 6? What's that? You couldn't tell me, right? But you're probably going to say it's probably somewhere between 2 and 3. Okay. And this is where logarithms come into play. Logarithms allow you to work with exponents, bases and exponents. And what we get here are a couple of different formats. What we're going to talk about today is what's called logarithmic. I think this is all spelled incorrectly. So log form and exponential form. Logarithmic and exponential form are going to be basically synonymous with one another. They mean the same. And it's really, really easy to show you with simple numbers. Oh, I thought it'd be easier. So if I do this, if I say logarithms have what are called bases. We say log base b. Log base b of y equals x is the same thing as saying b to the x equals y. Okay, they're equivalent statements. So if you go back to the idea we just had a second ago where we wrote 2 squared was 4, is that logarithmic or exponential? Exponential. It says this 2 was my base, the other 2 was an exponent, and it equaled some value 4. So exponentially, that would have looked, 2 squared equals 4. So I could say that log, let me move this up a bit, log base 2 of 4 is 2. So we're going with that? They move back and forth. Same thing with that 2 to something power is 6. That means the log base 2 of 6 is something. What that something is, I don't know, but we'll be able to figure it out here pretty quick. It's called logarithmic form, and it's how you solve for exponents. Chemistry uses this. If you haven't seen it yet, I know that chemistry it might be AP Chem that uses it more than regular or honors chem. Because I remember one time a couple years ago, when my wife was teaching AP Chem, in case I didn't tell you that, when she was teaching AP Chem, she came home. She goes, "Why the hell do you have to have logarithms everywhere?" She's yelling at me because it's my fault that science uses math. Sorry. It's always my fault. It's fine. I'm good with that. So, like I said, you get these 2 things that are called log base b of y and I know we just wrote this out. They're equivalency statements. Excuse me. Choking on carrots. Now, when we say this, the base will be written out for you, like log base 2 of something, log base 6 of something. This base was always given to you with some value, unless it's a log base 10. Log base 10 sometimes is written as this, just plain old log. It's kind of like when you have a variable that doesn't have a coefficient. That coefficient is always 1. So log base 10 is usually written as just log. Okay? So if you see just log, it means it has a base of 10. Does that make sense? It's kind of it's all weird. It's quite a log. I'm sorry, I didn't hear you. My ears are clogging. For the base 10? Yeah. Okay. Back in my day, there was they didn't have calculators that changed the base for you. Your calculators, and I'd say it was probably the past 6 or 7, maybe only by 6 or 7 years, we've had calculators that actually changed the base for you. Whereas when they were in log base, if it was a log base 6 problem, you had to do something that was called change base formula, Whereas a lot of other, it's button pressing, but it's tedious and it's really easy to screw up. So now that you don't have to really worry about it. Is that kind of what you're looking at? Yeah. It's just different ways of adding things. Now, there are two properties of logs that are used all the time, and they're super, super easy. Log base b of 1 equals 0, because what is anything to the 0 power always going to equal? 1. And same thing is log base b of b is 1, because what is anything to the first power? Itself. And those two properties are going to come into play here later on. We do a little bit of graphing with it, because when we graph logs, you only need 2 points. And those 2 points are going to be generated because of those two properties. It's super easy to see how this works. If I say that, oh, wait a second here. I'm actually right on this workforce so Devin can see. Hi, Devin. Did you shovel your parents' driveway a lot this weekend? Nice. Did you use geometry? Did you use any logs to support it? Screw you, Murphy. I'm out of here. Did he really leave? That's awesome. Hey, go, Devin. He's going to sneak in about underneath the camera and pop right back up. Or he's going to walk back with a log. Anyway, if I have log base 4 of 1, that equals 0. Because what that really is saying is that it says that 4 to the 0 power is 1. That's what it says. That's what that means. So, yes, Cam. It's not. This is a log format. Log base 4 of 1 equals 0. Now, when you see that, when you see a 1 in this position equaling 0, that means that the base is raised to that. Because remember, these two are equivalent. They mean the same thing. It's a different mindset with logarithms because you're not used to changing values across the equal sign without doing an operation, really. Okay. We're just using the logarithmic form and exponential form are inverses of one another. They undo each other, so there's certain properties that allow this to work. Okay. Believe me, a couple examples, you're like, oh, that's... You'll pick up on a couple of the tricks, too. For example, speaking of examples, if I have, you know who's going to do it. Devin tried to scare us. It was pretty funny. Yeah. So if I start with this, guys, if I start with the first one, it says log base 2 of 32 equals 5. That's log form. If I want to write that as an exponential form, it would be 2 to the 5th equals 32. Okay, that's kind of what we're talking about. We're getting used to the differences between going from exponential form, which we're used to seeing, to this new format of log. Okay. The next one says log base 5 of 1 equals 0. Exponentially, then, that means it is 5 to the 0 equals 1. Okay. Remember those the formatting there where you have log base b of y equals x is the same thing as saying b to the x equals y. That's what we're looking at right now. We'll do this switch back and forth quite often with these. So log base 5 of 1 equaling 0 is the same thing as saying 5 to the 0 is 1. Okay. The next one, it tells you it's log base 10 of 10. Sometimes it'll put the base 10 there. Sometimes it'll just say log of 10. It means the same thing. That one has a base of what? Oh, I'm sorry. And log base 10 of 10 has base what? base 10. So if I wrote that as exponential, it would look as 10 to the first equals. Now's where things start to get a little weird. Sometimes the textbook uses decimals with these, and sometimes the textbook will use fractions. Obviously, I'm going to say fractions are going to be a lot cleaner to see how it works, as opposed to the decimals. But remember, 0.1 is the same exact thing as saying what? Correct. So if I see that as a fraction, if I rewrite it, that means it's 10 to what power? 10 to the negative 1. What's 10 to the negative 1? It's 1/10. See where that's going? One of the other things you're going to see is that when you have fractions and whole numbers mixed together, there had to have been a negative exponent that happens. And we'll get into that more. Same thing here. See, I have a fraction for a base and a whole number in there. So if I have, oh, by the way, you can have fractional bases. It's not a big deal. So log base 1/2 of 2 is negative 1. That just means it was 1/2 to the negative 1 is 2. Remember, negative exponents create fractions by flipping them back and forth. Okay, that's the little trick you'll see. All right. What's wrong, Nelson? What's that? Oh, now you see why they work back and forth? Usually that's what happens when you see the fraction one. You're like, oh, flip a Rooney. Flip off a Rooney, if you know anybody that's a Rooney. It's big, it's heavy, it's wood. Do I need to do more of those? Yes. Let's do one more. Let's do log base 1/2 of 4 equals negative 2. I want to rewrite that as an exponential form. So if I have log base 1/2 of 4 equals negative 2, when I write it as an exponent, it's going to be 1/2 to the, yep, bless you, 1/2 to the negative 2 equals 4. Not bad, is it? Okay. Okay, maybe. I apologize when I tried to type this one in. Didn't look. People were having a hard time with the 9 there. So this is log base 9 of x equals 1/2. Yeah, it's not log base g, right? So now, if I wanted to solve for x here, what format would it be easier to solve for? An exponential, because this means 9 to the 1/2 power equals x. What's 9 to the 1/2 power? 3. Square root of 9, you get 3. Okay. Simplifying of these things and working with logarithms, you should not need a calculator because they're going to give you values that will be clean. All right. In order to make the properties work, they have to be clean. Otherwise, it's just awful. Don't get me wrong, we'll have awful stuff eventually, but not right away. Not terrible? Not yet. Evaluate. This is the idea where I'm going to ask you to simplify them. I'm going to ask you a lot of times to do some simplifying here. Log base 3 of 81. Now, it's not saying what it equals, it's asking you to figure out what the answer is going to be. So in the back of your mind, keep asking, keep thinking. When it's log base b of y, you should ask, b to what power gives you y? It's always easier to think in terms of exponential form than it is to think in terms of logs. Because you have to do a little bit, there's no calculator. You should know how to do this. 3 to what power is 81? 4. Because what's 3 squared? Square that, you get. This is 3 to the 4th power. Is 81. Okay? So your answer would be 4. Here's another tricky one where they give you a decimal. 4/100ths. It's going to be a lot easier to see that written as a fraction, isn't it? Not 4/10, 4/100, which is 1/25. So in your mind, you're thinking 5 to what power will equal a 1/25, which means to go from a whole number to a fraction, the exponent has to be negative. It has to be -2. -5 would be a lot bigger. Yes. Thank you. You're not going to die with these things. I doubt it. You never know. It might help you grow. Sorry. He said it could make you decay. Yo, you just figured my bad humor on the growth and decay of that. Again, yeah, see how you're going from 1/2 to some power. It's going to give you 8. When you start with a base that has a fraction and you're going to a whole number, that means your exponent has to be negative. Same thing goes for if you start with a whole number and your answer is a fraction, it had to be a negative. So 1/2 to what power generates 8? -3, very good. And then lastly, I know you're supposed to right now. Give me 1 second. I'll put log base 9 of 3 on a separate sheet. This one's a little tricky. Log base 9 of 3. 9 to what power is 3? 1/2. So it wasn't that tricky. Just trying to build it up a little bit. Okay. Now, one of the other things that's going on here, guys, one of the other things that's going on here is that in order to be simplifying these things through, you're actually using some other properties. For example, if we go back and I look at the log base 3 of 81. If I look at log base 3 of 81, you guys told me that this was equal to 4, correct? So that meant that it was 3 to the 4th equals 81. So in my mind then, what if I did this? Log base 3 of 3 to the 4th. What did I do to that 81? I didn't reduce it. I rewrote it into a base of 3. Because when I rewrite, if I can rewrite something into the same base, the exponent drops. Because there's a property about logarithms. Log base b of b to the x equals x. When you have the same bases, they undo each other. They're automatic inverse properties. Okay. Log base b, so log base 3 of 3 to the 4th is always going to equal 4 because those two properties undo one another. Okay. Same thing goes for if it was an exponent. If I have an exponent of, let's say, 3 to the log base 3 of 4, these two are the same bases, the answer would be 4 because they undo each other. They undo each other. So you have two properties in logarithms that use this. Let me write them out again for you. Excuse me. Log base b of b to the x always equals x. And b to the log base b. This right here is something weird looking. It's called exponentiating. It's a way to solve equations It's a way to solve equations that have logarithms. It's how you undo a logarithm to two sides of an equation to solve for x, basically, is what I'm getting. We'll get to that maybe very first of next week. All right, very first of next week. Not Monday, because we won't have Monday. First week. All right. Now, when you see these things, this is another thing that we'll be able to do, is that we'll be able to take certain equations, certain setups, and you can simplify and solve stuff kind of the same way. So, excuse me, if I have those two there. Oh, I'm ruining it, sorry. 10 to the log of 2 what's the base of the logarithm? 10. And why is it 10? Because it just says log, which means it has to be a 10. So 10 to the log of 2 is going to equal 2. Not y, that's log base b of y. Base 10, base 10. This is the property of b to the log base b of x. When these two are the same, your answer is whatever it was. They undo each other. Exponentiating a logarithm undoes the bases, and it leaves you with what the value is. Same thing with the next one. Log base 3 of 9 to the x. In my mind, I got to figure out a way to rewrite 9 as a base 3. 3 squared. Okay. It's 3. I thought you said squared. I'm like, yeah, 9 to the square root, but that won't give me a base 3. But I can do this. Log base 3 of 3 squared. Then it undoes itself. Your answer would be 2x. Because these two bases undo each other, the exponent just drops. Yes, ma'am. That's solving for x. We don't know how to do that yet. All it is simplifying. It's just a straight simplify. Huh? Channel. Oh, it's guys, stop for 1 second to give you another example. You guys. Sorry, that was loud. What's log base 2 of 2 to the x? X. Yes. Log base 2 of 2 to the x. Those two bases are the same. They both are base 2. Undoes one another. They undo each other. Leaves you with an answer of x. 7 to the log base 7 of x also happens to simplify out to equaling yes, sir. It's log base 7 of x. What's that? No. That's the same thing as saying this. Log. That's what that says. Yeah. Yeah, Colby, that's what this is. It's what it looks like. Sometimes it's tough to see with the fonts. Or the fonts. See what I did there? I know. All right. What's log base 25 of 5? So you're all right. So again, what you're saying is 2, right? So that means you're saying that 25 squared is 5. Remember, remember equivalency forms. Okay. Remember equivalency forms. Now, excuse me. Log base 6 of 1. Remember what that means. It means 6 to what power is 1? 0. Properties is why I put them back in there so you don't forget those. They come back and forth all the time. Guess what? There's this thing called natural log. Those are trees, in case you're wondering. No, not all of it. So what we have normally, what we do here is this common log is when you have log base 10. It's the same thing as log of x. That's what they call a common log. Guys, enough. I have a lot more to get through, and you're still doing all the homework. So you have this thing called common log. Common log is the idea where you have log base 10. When you have log base 10, they just don't write base 10. Sometimes they do, sometimes they don't. It's just remember, if you see something that doesn't have a specifically written value for the base, it is implied that it is base 10. Same idea as when we talk about coefficients of values. If there's no number in front, it means that the coefficient is 1. It's the same basic principle. Sometimes when you have a base, you could have what's called log base e. Just like we've had before, we had e to the x. We have e problems for the continuous growth models and stuff. We had the PERT, p times e to the rt. Log base e of x is the exact same thing as what's called log of the natural. There's a button on your calculator that says ln. That stands for natural log. It's log of the natural base is technically what it's called. That's why they came up with the ln button. And those are equivalent. Log base e of x, see it, Evan? Equals the natural log of x. These two are equivalent statements. So natural log, if you see ln of x, it means that it's log base e of x. All right, just so you guys know. They will try to mess with you a little bit with the natural log stuff. But once you get accustomed to seeing it, it's super, super easy to work with because it's the same thing. Okay? You would treat it the exact same way as if this was a 6. So if if it was log base e of 1, what's your answer? Well, what's that simplified to be? 0. Well, then we would worry about it later. But I'm just saying that the properties, it just means that the property is still the same thing. E to the 0 is still 1. That's all I'm getting. You treat it like you would in anything else for now. We'll worry about when you don't have 1s and 0s because then you just got to press buttons. We're not there button press yet. That's easy. That's super easy. Okay. It's just adding another step to solving an equation really all it is. Okay. Which means we can do this. We can do some graphing. Yay! So this is super, super easy. Just like we have had many, 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 many times, we had H's and K's. H's and K's shift horizontally and vertically, just like they have in the past. So this is what a shift would look like, which means that I'm going to have what's called a parent function at y equals log base b of x. In the past few times that we've done graphing, we have graphed via usually 5 points, -2, -1, 0, 1, and 2. With logarithms, you're using 2 points. You're going to use the property. All you have to worry about for the graphing these things are the properties of log base b of b is 1, and log base b of 1 is 0. That's how you generate ordered pairs, and then we shift them. There are only 2 directions that logarithm graphs can go, up and right, down and right. And it all depends upon the b value. Your b value, if it is greater than 1, the graph moves up and right. If it is fractional, between 0 and 1, it moves down and right. You have domain values. Domain, remember those are your possible values of x. Domain values will always be larger than whatever your h is. Your h value is always encapsulated in the parentheses, just like it has been for every other h and k problem we've had. And also you have, excuse me, a vertical asymptote at whatever the h value is. This sounds really, 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 really weird to do, but it is so simplistic. That's why I know, even though I only have about 10 minutes, I can show you and you guys can go, really, that's it? And I'll say, really, that's it. Really?
Will b always be positive?
Yes. Yep. And that's why it goes pretty quick. So if I'm looking at this, we'll use this as an example. Move this up just a bit. I have log base 1/3 of x minus 1. First thing I'm always going to do is label my my base, my b, my h, and k. Because remember, your h tells you where your asymptote is, and it tells you where your domain is, everything to the right of it. Your h is always thrown in parentheses. Do I see anything thrown in parentheses here? So what's your value of h? 0. 0. If it was 1, it would have been that. Oh, sorry, it would have been -1. It would have been in parentheses. Since there's nothing in parentheses, there's no h. So my base is 1/3. My h is 0. And then my k is -1. The other quick thing that I do real fast here is knowing that my b value is fractional between 0 and 1, I know my graph is going to do this. So I put a little sketch. Remember we've done that before where we looked at our sheets if it was going to be like which direction was stretched for an ellipse or a hyperbola or something. We did the same idea, so we knew things would match up. I do that here also, just so I get a quick little glimpse of the way I don't screw something up. So that means that my parent function here is just log, excuse me, my parent is going to be y equals log base 1/3 of x. We all right with that? Which means then I'm going to use these 2 properties to generate ordered pairs. One of my values of x is going to be whatever my base is, and my other value of x that I'm substituting is going to be 1. What's the base of this problem? 1/3. So my parent graph is going to have ordered pair at 1/3, and I'm going to have a parent graph ordered pair at 1. I know that right away because of these 2 properties. So if I substitute in log base 1/3 of 1/3, what do you get? I get 1 because the property tells me so. And if I use log base 1/3 of 1, what does the property say that has to equal? 0. See how fast that is? You don't have to really think about much. You just have to remember the 2 properties. So when I go to plot stuff then, let me do this. When I go to plot stuff, where is my asymptote going to go? Yes, ma'am. For this one? Oh, remember the property? Anything of any log base b of 1 is always equal to 0. So if I choose x to equal 1, log base 1/3 of 1 will always equal 0. Yeah, it's because I was using those up there. So I know that I have an asymptote at x equals h. So my asymptote is at x equals 0. And my first order pair is at 1/3 and 1. So if I say this is 1, I put 1/3 about here. I'll put 1 here, so we'll say here-ish.
Yeah, sure.
And then at 1, where do I put it? At 0. This graph is moving down and right, so all I have to do is this. No horizontal asymptotes, just a vertical. Okay? It's just a vertical asymptote. H. Whatever your value of h is. You always have a vertical asymptote. At x equals h. Always. In this case, it's 0 because there's no h value. To each of those ordered pairs, then, if I have parent at 1/3, 1/3 and what was it, 1? And then I have at 1 and 0. My shift was a vertical shift of -1. So what do I have to do with each of those ordered pairs? Bring them down 1. So it'll be at k value. Yes, ma'am. What's that? I use the property log base b of b equals 1. Anytime you have any log base of it the same value, it always equals 1 because what is 1/3 to excuse me, what is 1/3 to the 1 power? 1/3. Okay, that's why we're using those out. So then my shift, all I have to do is subtract 1, it'd be at 1/3, 0, and 1, and -1. And this is a solid line. All you have to do to graph. Label, parent, shift. Graphing log graphs, they look like they're going to be awful, but they're probably the easiest graphs we do. Because they're 2 ordered pairs. That's all you need. Yes, ma'am. Mm-hmm. Yep. And if the h value was 5, I would add 5 and move it to the right. If the h value was -5, I'd move it to the left. Okay? And that's what we're looking at doing. Excuse me. Real fast. If I have, just for giggles here, I have a log base 6. What are the 2 ordered pairs you're going to use for that? What's one value of x you're going to use? 6. What's the other one? 0. Your ordered pairs if you choose would be 6 and 0. I'm sorry, 1. I was thinking I was going the other way. It'd be 1, 6 and 1. Better yet, you're always going to use 1 for one of the parent functions. The other one will always be whatever your base is. Yes, sir.
So for that, we always.
Yes. It's kind of nice. Kind of really nice. Yes, sir. Correct. Well, the one of them will always be this. Yep, one will always be at 1 and 0. The other one will be at whatever your base is at 1. Because of the property. Log base 6 of 6 is 1. Log base 6 of 1 is 0. Because by using the properties of logarithms to go back and forth by the 2 quick ones, you get 2 ordered pairs real fast and you know general directions of your curves, you plot them. So your ordered pairs for these things for a parent function, you're always going to have b and 1 and 1 and 0. Those will always be your ordered pairs for your parent function. 2 of those, you just move them. HUK. I believe I already put the problems on the internet because I forgot to do it earlier. It's 490. It was. Yeah, that's not far right. I will recommend one thing when you when you start doing your homework on the sheets of paper. I'm going to show you what I would put on my top page there. It was what 1634 even, and then it was 40, 48 to basically 66 even. Then. When I get my sheet, when I start putting my problems on my page, first thing I'm going to put up on the top here. Oops. So here's your whole sheet of paper, right? So here's where your name is and all that stuff. I'm going to put down log base b of y equals x, and b to the x equals y. I'm going to put in my properties. So I'm always looking back at them. I'm going to write log base b of b is 1, and log base b of 1 is 0. I'm going to put those quick properties on my sheet of paper. I don't have to go rustling back and forth because those are the ones you're going to use all the time. Okay? It seems like a lot to start with, but once you get cranking through some of these, I had a couple people in Flex from First Hour that were working on them just this afternoon, and they're like, "Is that it? Yeah, that's it. Really? Yeah. There's not much to start with. All right. You okay, Nelson? You look very, very upset. What do you want? Yep. For all your parent functions, you always have a 1, 0, and a 1. And that's what's great about logs. That's why it's so easy to work with, as far as the method is concerned.